All right, so we're going to be going over the Unit 1 practice problem set. And let's dive into this. So number 1, let L be the low temperature in Athens, Georgia for each day D in the year 2015. And we want to know, is L a function of D? And B, is D a function of L? Well, let's, to kind of make this a bit more clear, I'm going to draw a little picture here, or make a little table rather. Let's suppose that we're in January, okay, and let's have a D column, that's the day, and then we'll have a temp column, which is L. Okay, so we have the first, second, third, fourth, and so on, all the way down to 31. January has 31 days, doesn't it? I have to check that later. And then the low temperature on day 1, let's say that it was 13 degrees, and then day 2 was 14 degrees, and day 3 it was 13 degrees again, and day 4 is 27 degrees. I don't know. So now let's go back to the question. So can L be a function of D? Can L be a function of D? So that means that we need, for each input D, we can only have one output. So the input would be the day, and the output would be the temperature. So can you have more than one low temperature per day? That's the question. Because if you can, then you don't have a function, right? Because each input needs to have a unique output. So phrasing it like that, I think it's a bit more clear. You can't have on any given day more than one low temperature, right? So you're never going to have on the first day of January, New Year's Day, you're never going to have more than one temperature. If more than one low temp, if it's 13, if that's the low temp, then that's the only low temp for that day. So yes, that's okay. So we can have a function L of D. However, if we reverse this and we say, is D a function of L? So yes to this, but what about D a function of L? So that would be going this way. So can we have one temperature that corresponds to two different days? So one temperature going to two different outputs. And we can see clearly that you can have that. So you can have 13, that was the low temperature day 1, and 13 was the low temperature for day 3. So we can have one input with two different outputs. And so that's a problem that violates the definition of a function, and so the answer is no. Okay, let's go to the next set of questions. All of these questions are going to use this graph. So question number 2 says, explain how we can know that y is a function of x, where y is the vertical axis, the output here, and x is the horizontal axis. So we know that y is a function of x because it passes the vertical line test. And specifically that means each input has a unique output. And if we actually go over here and say, let's just draw an example, there's a vertical line. If you let this vertical line move through the entire function, you're never going to intersect the function more than once, and that's what we have to have happen in order for that to be a function. Okay, so yes. All right, what about number 3? What is the domain of the function? Well, let's assume that there is a little arrow here and here. If we had a picture that looked like this and there was a dot there, then I would assume that the function stopped where those dots were. But since we don't have a dot, we have an arrow. Well, actually, we didn't have an arrow. I added the arrow, but we didn't have the dots. Okay, so in this class, you can assume that if you have a picture, let me actually erase all that so you can see the original picture. If you have a picture that looks like that, then you can assume that this is the same thing as having the arrow there, okay? And so why is that relevant? Well, that means that this behavior continues and this behavior continues. And what's relevant to us is that this behavior continues moving this way and this behavior continues moving this way, because these are moving, this function is moving left, both left and right, as well as it up and down. So there's no limit on either side to how far we're going to go negatively or positively in the horizontal direction. And so that means my domain is all real numbers. And the way we write all real numbers is like so. Okay. Number 4, on the interval -6 to -4, what is the function doing? Okay, well, from -6 to -4, that's here to here. And so the function's clearly increasing. This arrow here, if that, you might look at that arrow and say, oh, it's decreasing. But remember, we always read left to right. So we're reading left to right. So as we move left to right, the function is getting larger. So it's increasing. And is it at an increasing, decreasing, or constant rate? Well, remember, this is about this is another way to talk about concavity. So right here, the function is concave down, and so the rate is actually decreasing. It is approaching 0. Okay, so this is increasing at a decreasing rate. It's leveling off. That's the thing to pay attention to. Okay, what about number 5? How many turning points does this graph have? Well, turning points correspond to local maxes and mins, and we have roughly a max around there, and we have a minimum around there, so that's 2. So we have 2 turning points. What about inflection points? So you kind of have to guesstimate this, but we're clearly concave down over here and concave up over here, and so inflection points are about changes in concavity, and so there is one change of concavity that occurs in here somewhere, and so that's one inflection point, a single inflection point. All right, does the graph have a local maximum? That's number 6. So we actually addressed this a little bit already. Yes, it does, and approximately, it's here, so I'm going to say approximately, I don't know, that's, if this is -2, we have 1, 2, 3, 4, 5 tick marks there. That looks to be at about the height 500. So let's say it's 2 point, oh gosh, let's call it -3, 500 as the coordinates of that point. Remember, this is an approximation. And number 7, how many solutions does the equation y = 100 have? Well, 100, 200, 300, 400, so each of these tick marks is going to represent 100. So 100 is like right there. So if I draw horizontal, I'm kind of drawing I'm trying to draw a dotted line there. So it's bending a little bit, but it's supposed to be a horizontal line. How many times does this dotted line intersect the curve? So we have one time here, one time here, and one time here. So that's 3 intersections. And so each one of those intersections is a solution to this. The idea being, y is this function. So basically it's like, set this function equal to 100, and how many solutions will you have? Well, you will have 3 solutions. Number 8, on the interval -2 to 1, the function is increasing, decreasing, or constant. Okay, let me clean all this up so we can see this a bit better. So from -2 to 1, that's here to here, somewhere in there, the function is going down, right? It's going down. It's decreasing. On the interval 1 to 3, the function's average rate of change is doing what? Okay, so from 1 to 3, let me mark this. There's 1 roughly, and there's 3. So basically we've got this little dip, and I want to know what the average rate of change is doing over this dip. Okay, this little cup down area. So this is concave up, right? The function's concave up in this region. That's concave up. It's decreasing and then it starts to increase. That's the function, but not the arc. The arc, what does the arc do? Well, the arc is always getting bigger. So the function decreases and then increases, but the average rate of change is constantly getting larger. I shouldn't even say constantly, that's confusing. It's always getting larger, so the function's average rate of change is increasing. Now that might confuse you a little bit because you might be thinking about increasing at an increasing rate and decreasing rate and all that stuff. But if I was talking about this in terms of rate, I would say that it is decreasing at a decreasing rate in this region, and then the function's increasing at an increasing rate. So that's confusing because I went from decreasing rate to increasing rate, but then I said the average rate of change is always increasing. Well, all of that is true, and that's just the fact of the language that we use to describe rates of change. The rate of change here is negative, but it's becoming less negative, and it's approaching 0, but then here the rate of change is going to exceed 0 and then become more and more positive. So that's why when we say decreasing rate of change at a decreasing rate, then it's leveling off to 0, but then getting bigger. So hopefully that's not too confusing. But numerically speaking, the average rates of change are always getting larger here, because if we calculated them, hopefully I'm not beating the horse too much here, but if we calculated this rate and then that rate and then that rate and then that rate and that rate, this might be like -3, and then this one might be like -2, and then this one would be like 0, and this one could be +2, and then maybe that one's +3. So this sequence of numbers is an increasing sequence, and that's why we say that the average rate of change is increasing. Okay, moving along. So we got one more question, I think, on this picture. So does the function have an inverse? Well, in order to have an inverse, it has to pass the HLT, the horizontal line test. So does it pass the HLT? Well, what that means is, can any horizontal line intersect the function only once? So if there is a horizontal line that intersects the function more than once, then we don't have an inverse unless we change the domain. And so actually, we kind of proved this already, that it doesn't have an inverse right here with this y = 100, because here I could draw this horizontal line, and I have multiple points of intersection, and so does not pass. Doesn't pass. So no inverse. Okay. So that's the first 10 questions. I'll pause the video and then we'll return and answer some more.